The shorter talk, I mean, should, in a sense, deal with, say, point of view of a nuclear physicist, like me. So it's much more, so of course I should be, it's much more specialized, much more restricted than the previous one. And say, I will talk specifically of the inner crust in the regime, say, typically, say, up to maybe let's say one third, 1/4, let's say, of the nuclear saturation density, where we can safely assume, say, spherical nuclei, and considering superconductivity, superfluidity, say, just pair neutron pairing in one S0 channel. So that by itself, say, excludes this fascinating regime of Pastor phase, simply because, I mean, just as it has been done many times, and said many times, it's such an involved and difficult problem. And say here, I would like to give you a flavor, say, of some microscopic studies that, say, involve and deal with inhomogeneous structure inside the Wigner-side cell. So, I mean, there have been in the literature, say, in the last, say maybe 8 years, let's say, 10 years, there's much effort, say, to go microscopically, and now I'm talking, say, about this nuclear structure physics community, which they have also a strong interest in this topic, also because of the great development in nuclear physics concerning, say, exotic nuclei, radioactive beams, say, really when you push nuclear physics to the extreme, the isotopic composition. So to make a comparison, say, between the realm of nuclear physics and neutron star is very fascinating for a nuclear physicist. And so, say, there have been studies in detail concerning isotopic composition of the Wigner-side cell, mean field potential, collective excitation inside the cells, superfluidity, specific heat, and other issues. And of course, I mean, this should also be put in a context where you also try to understand what are the limitations of Wigner-side's approach, and typically, say, for example, first studies of band structure, assuming a Coulomb lattice, that you want to study the effect of that structure, entrainment, effective mass, and the other properties, and I think the next talk will deal more with this. So I will be more focused, say, on this problem here, superfluidity within a Wigner-side cell. And I would like to ask, say, two specific questions. Say, what is the spatial dependence of the pairing gap? How important are the nuclear clusters compared, say, to a simplified image that, for example, is very much used in Coulomb simulation. Coulomb simulation, after all, when you look at the literature many times, the only parameter that really enters in Coulomb simulation is a gap. So is a pairing gap in the inner crust is a function of density. This, I think, is a typical ingredient when you talk superfluidity. Then you have all possible mechanisms, microscopic mechanisms that are studied, but the microscopic input that comes in is the pairing gap. I think it's useful for an astrophysicist to have a little more insight, say, what we mean in nuclear physics by superfluid gaps. So the gap, in fact, inside I show you, inside the cell, will have a spatial dependence. And I'll ask myself, what is the importance really of this, say, nuclear shell structure? And then I'd like to ask, say, are the gaps affected by many body processes? We know that most probably the answer is yes, but the question is also by how much. This is a crucial point, as you also, as I said at the end of your talk. Say, I would just said, commonly used approach. You have, say, this well-used so many times bell-shaped curve that everybody has seen so many times, and this is the gap. So what is the gap? The gap is the Fermi energy calculated, say, within BCS theory in neutron star matter, infinite system, homogeneous one. And the nice feature is that this, if you use a bare nuclear potential, here Paris are gone, this is a rather universal curve that depends on the phase shift in the 1s0 channel for neutrons. So this is well established. So this is a mean field, if you want mean field picture. It's very nice, well settled, and many times I'm doing just take this value as a function of density of Fermi momentum. Now, if you go more microscopically, say the typical structure inside a Wigner-side cell, so I repeat, I typically say 1/10 of saturation density. So typical Wigner-side cell will be maybe 30 Fermi radius. So I approximate it with a sphere. So that's the simplest way to look at the problem. And in this sphere, I will have, say, my nuclear cluster here that, of course, produces a deeper potential.
I'm sorry, what's nuclear cluster?
Nuclear cluster, I don't know, called, say, the ion at the Coulomb lattice will be, say, typically, say, a nucleus with 50 protons, typically. So let's say a thin nucleus with 50 protons, and typically, say, maybe 90 or 100 neutrons bound in a potential here. So you have typically 100 neutrons here. And then here you have a positive Fermi surface, value of the Fermi energy. So here you have many, let's say, very loosely bound neutrons that will feel the attraction of the nucleus here. But look, this nucleus, this cluster, as I said, this cluster produces a potential that is typically maybe correspond to the surface of 7 Fermis, 8 Fermis, and the volume is a huge volume, so it's 30 Fermi. So you have a region, rather small one, where you have a nuclear potential that is maybe 30, 40 MeV. This is for neutrons. The protons will have, here I will not talk about protons here. They will only there to stabilize the system, and you suppose that you have another well where you have 50 protons well bound, so they will not enter here because I'm only dealing with neutron superfluidity here. So is it clear? So here you have about, typically in this cell, maybe 1500 neutrons which are, say, free in this region. Of course, as I said before, this is a big approximation because I assume a Wigner-side cell. If you think that you have a crystal, then of course there will be block states, block waves, and you have to consider all the periodicity. But here, I said this is my assumption. I restrict myself to this simple system. So here, if I go back to the bell-shaped curve as before, I already see something. That when I'm here, so most of the volume of the cell occupied by neutrons, it corresponds typically, say, here, as I said, I have about 1/10 of saturation density, and typically it corresponds to a gap, say, of about 2 MeV. So the approximation here is to neglect, this thing here. You can say, oh, this volume is very small compared to the big volume of the cell, and one could roughly say, okay, let's use this value, say this average, I would take this average neutron density in the cell, and I use this delta, let's say, for some simulation, for something. Now, I would like to see, say, what are the consequences of the fact that here you have a much deeper local Fermi momentum. So, for example, you already see the pairing inside the cluster. I don't know if you want, I can call the nucleus here. The nucleus here would be, you're supposed to be much smaller in the volume, in this case, and higher on the surface. So you see, this is an inhomogeneous problem. And this has been attacked in the literature here by different groups. I just listed a few papers that belong to different groups. In Italy, say, at Orsay, in other groups, this is Milano, this is Catania, this is in Germany, these are other contributions. So typically, this is the only technical slide, but I need it to define my quantities, to define it. Because I need a quantity that depends on position. So actually, say, what these papers have done, they have solved, say, essentially the BCS pairing gap equation, only this is a more advanced, say, sometimes in the solid state literature they're called Dejean-Bogoliubov equation. Here, in nuclear physics, they're more called Hartree-Fock-Bogoliubov equations. And the pairing gap, say, is characterized when you have an inhomogeneous system. It becomes a matrix, essentially, that depends, or say, on two indices that tell you, say, what are the states which are paired, and they are not necessarily paired in time reversal if you start from a basis. But this is techniques. I mean, I just want to show you that you can define a pairing field with matrix element as this one in your basis. That depends on the center of mass of the pair, the Cooper pair, and on the relative distance. And this is the product of the effective interaction that you use in a simple case. This will depend on the distance, relative distance between the two neutrons that interact, multiplied by this Cooper pair wave function. It's called, or abnormal density. And this is the structure. It has a product of the UV factor that are related, say, to the occupation probability, like in BCS usual theory. Say V squared essentially is the occupation, and the wave function of your system. So the wave function of your system, what are they? The wave function of your system are the single particle states in this whole system. So some of them will be trapped in the well. Some of them will be resonance state, because you understand that you have resonance in the continuum. You have some shell structure. This will play a key role in some applications. And then most of the states, of course, are essentially free waves. I mean, inside the Wigner cell. So you use all of them, and it's nice if you think from the viewpoint of a nuclear physicist. If your Fermi energy will be here, then you describe an isolated nucleus. Then you raise the Fermi energy, and you can describe the situation of a, say, Wigner side cell in the inner crust of a neutron star. So that's why also this is fascinating for a nuclear structure physicist, because you can try to use simpler, say, similar techniques to deal with one problem and the other. So you just raise essentially the Fermi energy. Of course, you have to calculate the structure, you have to calculate the number of protons in the cell. But for our problem now, this is what matters. So what is the essential result of this calculation? The essential result of this calculation is, as I showed you before, that delta here is a function of two variables, the center of mass and the relative distance, or if you Fourier transform, of the relative momentum. You can show what you want. And typically, say again, you are interested mostly in the gap at the Fermi energy. At the Fermi energy means either that you take this matrix element here with n prime single particle states close to the Fermi energy, or you take here Kf, the Fermi moment, essentially. So this is, you can do both things. And what happens here is shown in momentum space. So if you look at, this is the most relevant curve here. This is a local density approximation, the one when you take the bell-shaped curve, and density by density you use the value of the gap, and you see what you expected. Outside, you get to about 2.5 MeV. This is the value in uniform matter. When you get into the nucleus, you go down with this interaction. It is a nuclear-nuclear interaction. But if you make a real quantum calculation, you see something that is well known, say from solid-state physics, you have this proximity effect. Say you have two regions, inside, outside, if you want two phases, split in phases, and actually the pairing gap will be raised inside and lowered outside, giving a continuous curve here, and this is just proximity effect in the sense. So you see the local density approximation overestimates the decrease of the pairing gap in the interior of the nucleus, and you have a smooth function. So this is the main result from this more detailed calculation of the pairing gap. So you, of course, the situation will change according to the density you are in, the potential you are, the number of neutrons. But if you want just to recall one single result from something that may not be familiar to you, it's just that you are able to deal with this non-homogeneous situation, non-local one, and then you can ask, say, different questions, say, asking what is really the relevance of this nucleus, say, because now you have a quantum solution of the problem. I remind you, as Dima told before, this inner crust is really quantum problem. It's really quantum system in full glory, so you have to use quantum calculation. Here I just show the effect in another way. Before I show in space, now I show in delta. This is the matrix element of your pairing field. This delta and n in diagonal plane. Here you have the Fermi energy, so you have an effect due to the nucleus. The presence of the nucleus, as I told you, decreases the gap inside, So the final result at the Fermi energy, it decreases for this cell by 5–10% the value at the Fermi energy. So these are the gaps. You should look here. Here is the Fermi energy. So here is calculated without the nucleus, here with the nucleus, and you see that at the Fermi energy there is about 5–10% difference, plus, of course, there is another effect, that if you think of an average density, the neutrons are segregated in the well. So this is a not subtle, it's a simple effect. I don't know if it's really included in the cooling code as they are at low density. When the density is higher in the cell, and in a cell you have 2,000 neutrons, you don't care. But when you have only, you say, 160, 200, 300 neutrons, of course it matters the shift of the Fermi energy. What I mean is that if you have typically 200 neutrons in your cell, and 150 are segregated in the nucleus, the properties, the thermal properties of your system are much more similar to a very dilute system with 50 neutrons. So you have to be careful about this change of Fermi energy. So these are the two main effects due to inhomogeneities. Now I would like to say, what are the consequences of that? There are two kinds of consequences basically, depending on the property you want to look at. If you want to go, say, to look at a rather global quantity that involves the whole cell, like for example specific heat of the system, then what turns out is that in this plot I show you going from this zero is the interface between, say, core and crust, essentially. When I say interface, really it's the beginning of maybe the pasta phase. So maybe 1/3 of your saturation density, and here you go towards the crust. Say, in a schematic, very schematic calculation, say this is the specific heat of your system with your nucleus and assuming uniform. Since the gap, as I show you, is lowered, the specific heat tends to increase, and typically what you find, I show you, it's a rather small increase. It's 5–10%. So typically, in most cases, you can find an order of magnitude, essentially. But, of course, there is another effect that is well known, that even if the system is so complicated, thermally, say, there is a basic thing, so this electron specific heat, in most of the inner crust, is the driving factor when we have pairing gaps of the order of 2 MeV. So here, in this region, you don't care so much if the pairing is of the amount that you find in BCS. You may care in the outer layers. And I compared also with the specific heat of an unpaired system. Of course, here you see, so you have two things. This modulates the pairing gap because specific heat, because you typically go from 2 MeV to maybe 1.8 or something. This is a detailed nuclear structure effect. But the big effect, of course, is when you go from a non-superfluid to a superfluid system. So this is a global quantity of the cell, if you want.
I'm just still a little confused with this picture. R equals 0 is the crust core interface?
Yeah, you go, so it's the opposite that you think. So so this goes towards the surface. So here are the surface layers here.
Okay,
and this is very schematic. So maybe you should go from here to here. This is what is really been calculated here.
Now, at near R equals 0, you have some spherical approximation to the pasta?
As I said, well, we don't really go to the pasta phase. So this 0 is not really the real crust core interface. You think more of the pasta spherical case. Yes, it is about that time. Because we don't calculate pasta, so this is really spherical assumption all the way. And of course, this bell shape reminds you of the general bell shape of the pairing gap, just reversed. The fact that here, of course, here you have, since here you decrease the density, you are decreasing the density. So here, the pairing gap is largest, specific heat more suppressed. Here you go to outer layers, smaller density, then smaller pairing gap. You remember the bell-shaped curve. So you go towards smaller density.
What temperature are you calculating?
0.1 MeV. This is 0.1 MeV. I don't know if this is clear for, maybe you see, when I go in the previous transparency, I'm going in this direction. From inside to outside, so I decrease the typical pairing up. And this detailed microstructure effect is a modulation of this driving.
What are the contributions that are being included in the specific heat? Is just the neutron or the neutron nucleus and
this is really, so this is the full calculation, because this is a quantum calculation where you have the neutrons in a complete system. So you don't distinguish in this approach really the neutrons in the nucleus and the nucleus in the Fermi sea. You calculate quasi-particle energies and you make a quantum calculation of the specific heat.
But the collective modes.
There are no collective modes because this is just, as I show you, this BCS mean field approach. So you have the quasi-particle calculated at the BCS level. So you do not have here the effect of collective modes. Not even if you calculate not superfluid, they are not included here. So this is consistent with what I said before. Now, I would like to contrast, before going to the second issue, I would like to contrast these global properties that I mentioned with other things. So if instead you are interested in, say, properties that are specific to the existence of the nucleus, and I'm thinking of, say, the dynamical vortices, of pinning, so this question, does, say, pinning occur on nuclei? This is really a crucial thing, to know the spatial dependence. So I made this example just to stress this difference. If you look at some properties, some global properties, this is academically important, I think, but it's a detail compared to another uncertainty I'm going to discuss now. But if you look at specific property that involves the nucleus, this is crucial. And on Wednesday, so this, if you want, just to be seen in context with the talk Weber rank on Wednesday, where this will be applied to the structural vortices. So like if you remember at least a couple of slides, so it will make it easy. And now, say, second thing was, this was a mean field calculation. What happens? Here we know that this is, again, the bell-shaped curve, but shown not as a function of Kf, but of neutron density. This is nice, maybe we are so used to the other bell-shaped, and they have shown in this way, so this is the previous bell-shaped curve as a function of density. But we know that in infinite matter, again, homogeneous matter, this has been shown so many times. There are so many calculations that give rather different results. This is one of the newest. There is another one now coming again from Trieste group that does something like that. And here depends, of course, on the way you treat different many-body processes going beyond midfield. Now, this would be a long talk by itself. I'm not going to do that. I'm just saying, this is infinite matter. So this is an ambiguity we are going to have. That's really crucial and basic physics here. But is there something typical, something more when you ask yourself what happens in the crust, not in an homogeneous manner? There are other effects that we have to take into account, besides, of course, the uncertainty, basic uncertainty we have here. And
yeah, but I think, one can rule out a number of these on the basis of
there are many
arguments. So
there are many things.
Take this
for
face value.
For example, many of these calculations are surely incorrect at low density, for example. At low density, one thing that we know for sure, well, you have investigated so much low density problems there, but I think at least there is a consistency that you should have between, say, the interaction we are using to calculate, say, the pairing interaction and the collective modes, for example. This is, for sure, is not always, say, at low density, relative low density. If you do that, you have this ratio, say, about 2 between, say, BCS and this polarization calculation. That should be, I think, more or less respected. Then you have other things here. Some processes are sure are not included here. And I think concerning this new Monte Carlo calculation, here one big question is, how are really collective modes included in this calculation? Are they included? In my view, what is really missing, there is not, as far as I can see in the literature, really a big effort to make careful comparison between different approaches, if this is possible. This has not really been done. So you have different groups which have calculated these crucial quantities, but you don't see really a calculation try to compare in simple models. There is not. This is a big problem here. But as I said, I'm not going to discuss this in any detail here. I'd like just to show you a couple of things. First of all, of course, this is something that you can easily expect. If you just assume that you reduce your pairing interaction strength, just close your eyes, just make a simple calculation here of the specific heat. This as a function of the density now going, say, from a low density towards the inner part of the star. This would be the specific heat shown before, only going in the other direction that I showed you before. This is a typical difference I calculated with the nucleus or without the nucleus. But here there is a big difference when you calculate this with essentially 1 MeV pairing gap, and you see, or no pairing. Again, the same curve as before. So you know that the specific heat, if you have the suppression, will play a big role. But this is if you want rather obvious. That doesn't add anything to your understanding. It just shows the possible consequences of that. So going beyond mean field, one simple way to do it is that just to say the basic thing is that you have to dress your quasi-particle with, say, vibration, with essentially mostly with collective state of the system, and you have, say, self-energy effect and the exchange of these phonons between your, say, neutrons in this case. This is a neutron pairing problem. So you have a pair of neutrons that can exchange phonons. What are these phonons? And they can absorb or reabsorb, giving self-energy and induce interaction effect. These are the basic diagrams that you would like to have. And I would like to comment something that the nuclear astrophysics may not be aware of it. Of course, there is presently a discussion also in nuclear physics about this effect. Because also in nuclear physics, this exchange of, say, collective mode should play a role. We in Milano, we've done several calculations, there are discussions, but for us, say, the basic effect, now this is quantitatively, it's completely open. But the main effect is this medium effect tend to increase the pairing gap, in sharp contrast to most of the calculation in uniform. Why that? Because in nuclei, in finite nuclei, just for a moment think of an isolated atomic nucleus, there you have the presence of a surface. This surface can vibrate very collectively. This is something you do not have of course, in homogeneous matter. And this gives rise to, in our calculation at least, to a rather strong source of attraction and adds to the pairing gap. So in our view, this exchange of surface modes, that are the equivalent density modes in our atomic system, which are P, we have a transition density that is peaked at the surface of the nucleus, couples well to the single particle levels close to the Fermi energy, in the atomic nucleus I'm talking now. And they, in our calculation, they give rise to a strong induced interaction. Something you do not have in neutron matter, this presence of the finite surface. This tells you already that this, isn't it an interesting problem then, the problem of this mode, of these couplings in the Wittgenstein cell, where you have a nucleus in some way coexisting with a big chunk of homogeneous matter. So you expect that the vibration of your system, there are remnants of the surface there, will play a role that is different from what happens in a homogeneous system. So this is a message, if you want. This is a qualitative, very qualitative message. And so these last slides concern, say, this problem, so how you can deal with this problem. But there have been basically two very simple approaches now in the literature, as far as I know. It's really a starting point, no more than that. One thing was made by Baldo and Lombardo, Sabenstein, Tolokonikov, and what they've done, they've simply interpolated in the crust between density functions. They say, oh, I have a density functional that takes care of this many body effects in homogeneous part, And then I can use a density functional approach for my finite nucleus, like vigezzi, for example, and match them. So they match them, they interpolate between them, but of course you may wonder there that, for example, the density functional that you are using for the isolated nucleus, you are extrapolating here in a situation that is quite far. But anyways, I have calculated the pairing gap in the cell using this method and using functionals that, say, include this or not include this many body renormalization of superfluidity outside. This is one approach. The second one we have tried in Milano, and this is in a sense more difficult because it really requires the calculation of the phonons. And now, when I say phonons, I'm talking about the vibration inside one single Wegener-Seitz crust. So I'm not talking about the ions. I'm talking, if you want, about the plasmons, about the vibration of the neutron system. So we have done it. We have calculated all this vibration, that is rather painful work, and calculated their contribution in a, of course, assuming some interaction. And just show you the basic result. The basic result is that this was your bell shape with the interaction that we are using. And this is, if you want, the inclusion, say, of many body effects. We also find the suppression here. And this is, say, the effect of having the clusters inside your system compared to homogeneous system. But what is more interesting for us is the spatial dependence of the gap. The spatial dependence of your gap is here. So at this density, this is suppressed, slightly suppressed inside the nucleus here. This is without many body effects in the cell here. When you say include these many body effects in a local density approach inside the nucleus, you see, in homogeneous system, these many body effects make your pairing gap vanish. They suppress the pairing gap completely. But when we are in the crust, so in the crust we should be here, very close to zero inside the nucleus. In the microscopic calculation we find that the pairing gap instead survives and has a sizable amount. Why? Because the vibration that we calculated for the mixed system have quite different properties compared to the vibration we find in the homogeneous system. So now I'm not, you don't believe, of course, the quantitative feature here, but it's a mess. No, you should not, of course, because we don't know how to calculate the homogeneous, so I'm not going to sell you something I should not sell. But this is a qualitative mess about the finite structure effect that you find in the cell by omni thing. I don't know, this is maybe complicated, but I mean, maybe later if somebody wants to ask, I can just. So
what is happening at the edge of the cell?
At the edge of the cell, I have a slide. I want to just make a final comment. I show you just a second here. So just the conclusion was that concerning the spatial dependence, I think there has been considerable progress since, say, this influential review, say about 15 years ago, where it was stated that even now, say that the spatial variation of superfluid gaps in the inner crust is not well understood theoretically, even in the absence of superfluid flow. So I think at least at the mean field level, this problem has been solved, within the approximation, of course, that I explained before. And in the talk by Barranco Wednesday, we see what happens when you have superfluid flow. So our main motivation is the understanding of calculation of pinning energy, understanding of pinning mechanism on nucleus. So that's why we are so interested. But I show you the influence of thermal properties. And the last one, well, just two things. What about the coupling to lattice vibration, to the vibration of the ions? Nobody. There are some calculation of them. For example, this was recent or rather recent one of the lattice energy, vibration of the lattice. But I only told you exchange. We have included in a rather involved way coupling to the plasma, say, to the vibration of the neutrons. But what about, they have rather low energy, and of course typical vibration I have included have maybe 3 milli energy. Here is 0.5, but the coupling, to calculate the coupling, has never been, not even attacked. I don't know. And maybe somebody can see from simple consideration that this is not relevant. This I don't know. And the last point is,
sorry, could you figure out the plasma frequency of the lattice omega?
this was calculated by McGarrett, and this is of the lattice, of the ions. Before, I was only concerned about the neutrons in a given static, say, Wigner side cell. We don't include the fluctuation of the lattice itself. So this was, in this sense, was a static approximation. And of course, we don't calculate band structure. And this is the slide I wanted to show to you. We said, what happens at the edge of the cell? Here is simply that we use boundary condition where we have, say, where the wave function vanished. And you will say, wow, we should not do that. Why? Because this is a crystal after all. But, you know, if the Wigner side cell approximation is alright, then this doesn't matter. If you go to small Wigner side cells, typically maybe 15, 20 Fermis, this has been discussed very much by Chamel and others, then Wigner side approximation really makes you a problem, gives you a problem, and your calculation starts to really to depend, as also Baldo has shown, on the boundary condition. But if you have this size, this was last slide, here, this is the calculation in the cell with three different boundary conditions, vanishing or the derivative or the odd derivative vanish, or even by, and you see, you can see the difference. This is a pairing gap in a Wigner side cell calculated, say, at the Fermi energy as a function of density. Just a box of 30 Fermi wide. So it's in, I might have used different boundary conditions, but as far as your experience goes, this is not important for the density we are approaching. So, and okay, so this is, so if you, I just try to answer something about point 2, 3, something about 4. One, of course, I left out this is a subject by itself. Superfluidity does affect the isotopic composition of the crust. This is known, I'm not saying anything. And last point, I say, maybe it's a general question, say, could we say through observation sense to state that the crust is really superfluid or it's really quantitative? And also now, say, a theoretical concept, something that is only based on theory. Thank you very much.
So about the last question, several of us have discussed this.
Yes.
Can observations prove superfluidity in the crust? I think the work of Ed Brown and Andrew Cumming, I don't know if proof is probably very strong, but it's very suggestive that they cannot get agreement with the thermal relaxation that they see in quiescent no mass X-ray boundaries if they allow this neutron-specific heat not to be exponentially suppressed. So they need to suppress the
To some
neutron
extent, at least.
exponentially. No, I mean, they really need to suppress it a lot to get agreement. And so I said, you know, there's a very robust hit of superfluidity in the crust.
So this hinges on, let's say, understanding, simulation
That-
or cooling.
On relaxation, you know, the crust
Relaxation,
gets
yes,
hot
relaxation.
and then it cools later, and there cannot be a huge specific heat in the inner crust.
How do we think, even qualitatively, about pairing gaps for pasta?
This is, I don't know, this is something we have really not dealt with. Maybe Chris, you thought about that.
Well, I mean, one uses the same machinery, but we do with a different geometry. So. Or even,
If you assume, yeah, you say,
right, I mean, it's just some way cylinders are easier to deal with
just the same
than
reason.
spheres.
And the qualitative.
Plates are even easier.
Maybe if you have some specific, yes.
Right, so I mean,
But you have to, yeah, I don't know. You discussed
I
it
don't know
last
what
week.
sort of
I don't
answer
know
you
what
wanted,
is
Chuck.
status now.
Chuck, tell him what answer you want, and then Chris can explain how you get it.
They're kind of small in my classical dynamics. Yeah, I think we should have a betting pool, whether the gaps are big or small, or
I don't know if there
what
is
sort of
a...
expectation should one have.
But I was not here, no, I was not here last week, so I don't know what the concept. I don't know. To my view, there was not a really consensus about the structure one should calculate. Say it's simple once you know. I have a given geometry, then I do the same kind of calculation. But is there? What you have to do last week? 1 minute or 30 seconds.
Right. Well, I think last week we spent quite a lot of time talking about how you deal with the pasta and the transition from some part of the core that we might crust that we might understand to the core, and I think we all agreed that we didn't quite know how to do this. But one thing that, from my perspective, is quite important is the fact that many of the things that we're trying to model are relatively large scale, what I would call the hydrodynamic scale, and that's where most of us, when we do actual neutron star modeling, that's where we operate. And then, in order to get to that scale from any microphysics calculation, be that of the pasta shapes or transport or whatever, you need to do some averaging. And so that is relevant, I think, in all these things. And I think what we discussed a lot last week was, in the case of the pasta, where you might not expect on the larger scale, the various arrangements to actually prevail, you want to carry out some averaging. So. And the question there, I think, is that something that one could think about or do? And the same is true here, I think, for the gaps.
But I think that the gaps, the averaging will be relatively unimportant because the scales for coherence lengths are probably shorter than
any scale you would
disorder length
right.
for the structures. So of course, when we look at things like elastic constants, then it's a completely different story.
But I think it's also an illustration. We come from different camps or different sub areas, I guess, in many ways, and it's I think important to understand from, say, my perspective. I need input into a relatively macroscopic model, and the question is, what is legal? What are you allowed to use? From the microscopic theory, what should you really be, what are you manhandling in a terrible fashion if you use that as inputs? I think that's pretty much what we concluded after a week.
Because from our viewpoint, I mean, for us, it would be useful to know. Well, look, I mean, just from what you say, you could assume reasonably, say, this structure for the pasta phase. Then, of course, as he said, then technically it's not the point here, not the technical point. It's more for me. The physical thing to understand.
There may be an additional simplifying factor in the pasta phase because the number of nucleons is so large, the shell structure effects may not be the dominant ones. It may be that there's a Landau-Ginsburg theory that you can write down for the gaps. And you put some kind of background potential created by a proton cluster, and then you have a simpler set of equations rather than the HFB equations to solve for the gap and the radiation.
To make life much simpler. You wanted to ask?
Yeah, but also an interesting question is when you have the transition from the singlet to the triplet pairing, and that may very well happen in the pasta phase.
Yeah. So.
Because one of the things I looked in the nebula water, people have the last nucleus they calculated, something like germanium, something. The neutron densities they get is 0.12 per cubic Fermi.
Yes.
This is.
But if you look at the work of Freeman and Spink, they predict that because of induced interactions, the 3.2 gaps will be severely reduced.
Would be severe.
But I don't recall what density they stopped calculating.
So pasta will be normal with no gaps?
Maybe,
Well, but you will start running into trouble with things like the glitch data, like where you need about 1.4% of the moment of inertia to be in the loose screw component. And so if you start suppressing the gaps, and much of the neutrons are normal in the crust, then you would be in trouble. Unless you now bring
pasta around neutral matter density.
But the pasta,
Even the Swiss
no, but
pasta
the pasta is in the high density region, so it's a lot of the moment of inertia is tied up there, in that region. So I don't think you can suppress the gap too much. I don't know, I haven't done that. Many could know, but he's not going to say.
Well, maybe you can put constraints on what the upper density where superfluidity to prove out should be.
I was thinking about it, and I was thinking one might be it might be interesting to combine that kind of constraint for a generic type gap and just say, well, how far am I allowed to go in just drawing a generic type superfluid gap, assuming that it's the cross superfluid that does the glitches, and combining it with the cooling kind of thing that Brown and Andrew were doing. So I think one might be able to do that.
So there's two gaps, right? There's the gap inside the pasta, and then the so-called neutron drip outside. I guess we're talking about, when Danny talked about the high neutron density, he was talking inside the pasta. So there would be, it's the question, the cluster is not superfluid, but the matter surrounding the cluster still has a lower density, and you would predict a 1s0 gap there. So from the point of view of
I see.
But on the lasagna phase, half of
Yeah.
it is in crust, or half is
Of
outside.
course, the advantage of this
Oh, I
approach
see.
is that you really make, in this simple case, you can make really a full calculation, of course. You don't distinguish, say, different phases. This is really the advantage of this,
So
in a
is it-
simple case. Then you start to distinguish different phases.
But is the interaction in these models able to produce a 3p2 gap in the high density neutron matter? If you just ran this calculation assuming that your proton cluster produced a much deeper well, so that the kf of neutrons in the center of the cluster was actually large.
So maybe
It'd be interesting to see if there is an attractive term in the 3p2 channel, then you will have a transition from 1s0 to 3p2 pairing as you cross into the cluster.
that would be.
But aren't most of the interactions one uses for these lower density calculations so crude that they don't have all the spin orbit and whatnot? I mean, whether it's 3p1.
Yeah, but this is this is 1s0 channel. So everything is.
So I think it's much too crude to make or the
But it's
interactions
simply
used
different
at the
channels.
level that they're down to too crude to make predictions.
The
on
question,
the two
and
gaps.
then maybe we should move on and then discuss after lunch.
What about neutron emission? Then things like this affect
Even a very small
neutron
thing.
emission. Neutron Cooper pairing. Perhaps it is a question to Sanjay.
Yeah, so in fact, Danny and I were talking about precisely this point. Even if there's a tiny 3p2 gap in the
Yeah.
cluster, it's very important for neutrino emission. And, but first we have to say that qualitatively we expect a 3p2 gap somewhere in the crust, in these pieces of pasta. And the smaller it is, it may actually be more efficient.
I suggest nobody is allowed to talk about pasta until I've had lunch. Well, hopefully, no. Okay, we have one more drink today.
And then on again, immediately,
The what? Oh,
because then there will be different files.
Okay, so I'm going to speak about superfluidity, different aspects of superfluidity, which is more related to the dynamics of superfluids. So we have heard that in neutron stars there can be several superfluids, neutron superfluids, proton superconductors, hyperon or whatever. And we also know that neutron stars are not static objects, but they are evolving, and they can undergo various kind of instabilities, like this